and it shows the light curve of the first light curve in your CSV file, and that is why in my the standard best practices, I put the target as the first aperture that I put down. So to find this occultation, I'm going to say, I'm going to look for any event that's got at least 2 that are down and up to 20. So that looks for all events that have a duration that are at least 2 readings wide and up to 20. And it doesn't take long to find that event. Let's zoom in on it a little bit. And so it is located the event. The next step, I would do a report write. And I would take a look at that, and I would look at the false positive report, and I would discover that this was the drop that was found, and it is way above the drops that were found by running 50,000 trials looking for all drops that had a event size of 9. So that's what the false positive calculation does. It says you found something that was 9 readings wide. What is the possibility that that came from just noise? And by taking the noise, which is this part, everything except the occultation, I analyze that noise both for its sigma, but also for any correlation. You normally have correlated noise, which is a little chunkier and a little more likely to generate spurious drops. So it's this is probably one of the more important regions where the use of correlated noise is important. So given that the event was 9 readings wide, I generated 50,000 pure noise light curves, and I said, find the biggest drop you can find of a 9 wide event and apply the straight line criteria. It's got to be significantly different from a straight line solution. And when you find those, please record the drop that was found. So what this plot shows right here is that if it was just pure noise, the most likely drop that you would find if you did 50,000 trials with 9 as your duration was something about, 25,000, but we were up at like about 95,000. So it is highly likely that this event, that this drop did not come from noise. I hate to hear people say, aha, the event is confirmed. The PyOTE false positive says, I had an event. I grit my teeth because it doesn't say you had an event. It says that this drop was unlikely to be due to scintillation noise. It could just as easily have been a cloud event. So that's just a nit. It's just a little loose language. And I really hope that people get used to saying that the false positive says that the drop I saw probably didn't come from noise.
Bob, this
Um,
is a good segue into that report language that you put in recently. You might just scroll up to that on your report.
let's just take a look at it. I did add this. Let me see if I can highlight this so you know what I'm talking about. I added language to remind people that that false positive report simply says all PyOTE is saying is that that drop was unlikely to be an artifact of noise. But there are but specifically the second line says it does not prove that the drop is due to an occultation. It could easily be something else. And that's where observers and other things come into play. And in particular, you would want to take a look at your reference curve to see if anything happened in your reference curve. So I just added the reference curve to my display. Let me just zoom in on it. And we can see that the reference curve, which was green, does not have something similar to what was seen in your occultation. So that strongly suggests that it's not due to a cloud event. Um, Certainly not a cloud event that affected them closely. I just want to comment a bit now about the use of normalization, because it's quite possible to say, let me add a smooth that secondary, and I used 101 as the number of points. Let me just see what this was. Um, what was the time frame being used here? Oh, the time delta. So 100 of those is like 22 seconds. Um, so what we're following in that black line is effects that are on the order of 20 some seconds long. Um, those are likely to be scintillation and not due to any cloud effects. And I would caution anybody from saying, oh, let me normalize my target curve using the reference curve. All you are likely to do is take the noise from your reference curve and add it to your target curve. Let me show an example of when normalization becomes important. This is courtesy of Tony. He shared this with me, and here's a composite light curve where you can see he had 1, 2, 3, 4 comparison stars in addition to the tracking star. And here you can see that all of your light curves are being affected in some similar manner. In this case, you are wholly justified in doing a normalization of, I think this was the actual curve, the target curve shows an occultation. And here you will get benefit from normalizing against one of your reference stars. And here I would recommend using a reference star that is as physically close and as similar as possible in intensity to your target star. I think that this was what ultimately resulted from normalizing to one of those reference stars. And you can see, let me just zip this out of the way, you can see what the ups and downs, which are pretty significant, looked like. And normalization was effective. So use normalization, but use enough comparison stars that you can confirm that there is a justifiable reason for doing normalization. Otherwise, you're more likely to do harm than good. Okay, so at this point, I'd like to ask for questions.
George Viscomi.
Yes, George.
You can only normalize to one comparison star, correct?
At a time, yes.
Okay, thanks.
Now, in my light curve here, I only had one. Well, I guess there was another. I had the tracking, obviously. Well, that was no star. Here was the tracking. So I could have normalized to this. In fact, you can, but there's just no reason. There is no way to combine multiple reference stars into one to normalize against. I just don't see the logic. Normalization can be a powerful tool, but it can be very misleading as well. You know, don't use it unless you have a good reason, a good justification, enough curves that you can say, look, they've all been affected by some common thing. I'm going to use normalization to remove that common effect.
Bob, just want to mention that observing in the southeastern U.S., we're often affected by clouds and passing haze, small hazy areas. And so we often have sort of unstable baseline brightnesses of our target stars. And those are particularly, comparison stars, particularly useful in that circumstance because the clouds or haze affect both the target and the comparison star. And often that can elucidate an occultation. Whereas when you have scintillation effects, it only increases the noise.
The normalization was put into place in IOTA to deal with clouds. And IOTA has an additional capability which PyOTE does not, and that is to time shift the reference curve. If you have a cloud that is drifting across your star field, it will affect your reference star at a different time than it affects your target star. And so to do the best job of normalization, you really have to do a time shift in that case. PyOTE does not currently have that. It's something I could put in, but I just added the quick and dirty normalization as though the effect is one that affects all of your light curves simultaneously. Now, there are some of these things I've seen. Let me see, somebody had, I guess they were tracking and their dome began to obscure part of the light reaching their telescope. And so there was a gradual simultaneous diminution of the photons reaching their camera. You also can have daylight effects. You might have, you know, a car driving by on an unattended that somehow the light affects the background. Those are simultaneous effects. To really do a bang up job on cloud effects, I would really need to add the ability to time shift. Are there any other questions?
I have one.
Go ahead,
Uh,
Kai.
I noticed you, if I don't recall, if I recall, there's, and maybe you talked about this already and I missed it, drop frame detection in PyOTE. I've noticed it will sometimes ask me to confirm the times on certain frames. I don't know if it's due to drop frames or just potential for misreading the OCR timestamps, and it'll pop up the actual frames. And I believe that happens in PyOTE. Am I correct there?
That will happen in PyOTE if the video that was used to generate the PyMovie light curves is still on your computer and still in the same location. I will try to find it and I will show you that video, and that's a way to confirm that the timestamp information that is used for calculating the DNR times was in fact correct. And the value in that is that you could easily have had dropped frames, timestamps that were missing. But if the timestamps are correct for the two readings that were used for calculating DNR, that's all you need. And all of the other rubbish that happened in the meantime is irrelevant. So that's the reason why I went to that mechanism of asking for you to confirm. That's annoying for people who have timestamps that are always right, and so it is possible to disable that that pop-up.
That kind of segues into my next question, because I'm usually using fits where if having the pop-up show the header might be useful, but B, if the header's wrong, I'm probably, totally screwed anyway. I'm not going to have an OCR issue.
Yeah, you can suppress that. It's most useful for people who are using a VTI,
Right.
where the OCR can be a little shaky. Fortunately, the IOTA VTI has a very, very well defined font. It's really good for OCR. But there are other VTIs for which is not the case, and OCR can sometimes be problematic. PyMovie has ways of letting you kind of tune your OCR, but even when that is done to your best abilities, you can still have some frames for which the OCR was incorrect. But the saving grace is that once PyOTE finds the two readings that are necessary for calculating DNR times, if the OCR was correct for those two, then you will get good timings no matter what else went bump in the night.
Right. Okay.
Say, Bob.
Yes.
Dave Esper here. I've got a question. Occasionally you'll see like a single timestamp error outside of where your event is. You've got a positive, it's pretty obvious, and it's a ways out, maybe even outside of the immediate surroundings. And you do a block integrate. What happens with that one timestamp error? Because it seems like it's removed by doing a block integrate. So you got one bad reading, and after you do block integrate, you don't see that in the curve.
I'm not sure how to answer that. If it's just an OCR error, block integrate should work just fine. If you had dropped frames, now block integration has a problem, because where you're supposed to have, let's say, 8 readings per frame, eight readings in a group, now you will have, well, now you've got a problem. You might have one with only 6, and that means that all of the others are misaligned. So that's when you would start to have difficulty with a correct block integration. But if it's just an OCR error, it just rides right through that. The OCR, the little red line that I show, which says, you know, something happened here. The OCR timestamps did not advance as I expected. So I'm going to show you the area where that happened. If it didn't come from a dropped frame, block integration will work just fine.
Great. Okay. Thanks, Bob.
I noticed on the on those pictures, there's some very obvious horizontal lines of noise. It looks like a wood grain, and it seems to me that it ought to be possible to filter those out by using a high pass filter.
Are you referring to the PyMovie?
Yeah.
Let's bring that up. I think I still have it available. Yeah, they're here. This is something that is typical of the QHY. And I know that the Pluto group used QHY in their observation, and they did a row by row correction, if you will. And so they applied filtering and mean correction before they did any analysis. But for this, it didn't seem to, you know, cause any problems. But that is an artifact of the way the QHY row amplifiers do their job. I think it has one amplifier per row in the QHY. It has to do that to be able to be a high-speed camera. I think that goes up to like 1,000 frames per second, and you can only do that by having a row by row amplifier. Whenever you have an amplifier for each row, you've got to do something to deal with the fact that the amplifiers are a little different on each row.
Well, it also looks like if you compare two adjacent frames, the pattern also changes. So it's
Well, let's just drop back one frame. Yeah.
so it's
Yeah,
like
it definitely averages out over time from frame to frame.
Well, it definitely does. Let me just bring up the finder. Once we did a finder, it looked like this. You can still see some artifacts of that row by row, but mostly it's suppressed, which shows that on average. Let me just kind of amplify this. So even on a 400 frame average, you can still see that there is some residual row to row differences. I can still see some horizontal lines. And so that's why the Pluto group said, we're going to go through every frame and we're going to look at every row and we're going to apply some filtering and some correction. So your observation is correct, but it requires real diligence to to remove that, remove those effects. Simple high pass filter, I'm not sure that's what they did. I think it was more sophisticated than that. That's an academic setting, and they work very hard at doing the very best they can to get the very most information out of their recordings.
Bob, I believe on the newest version of Sharpcap, which is the capture software for the QHY, there is something in there that allows you to even out the lines. I have to run a version that's considerably before the latest, but I think there is something, whether it's good or bad, to even out those lines is a question, but I think there is actually something in Sharpcap that will do that.
Well, of course, the issue is it's a black box. You don't know what it's doing. Remember 3DNR.
Exactly. Yes.
It probably is doing a good job. The Sharpcap guy has been pretty much on the ball, but until he documents and tells you exactly what he's doing and what the side effects might be, just be careful.
Yes, I would prefer not to use it. So I would agree with you for the same reason.
I don't know how the time is going. I think I'm still in my time slot. Is there time for more questions?
Yeah, we, to be sort of obsessive compulsive about it, we have 4 minutes.
Okay.
Bob.
All right. Well, I did structure this so that there was more time for questions than the time for my formal presentation, because I really want to know what difficulties people are having with this.
I might just comment that it's not just the camera you use. I've got a very cheap camera that I've been playing around with, and it also has that very obvious horizontal line noise, and it's different for every frame. So my speculation is that it's just electronic noise. I don't know from where. Maybe from switching power supplies or something that's getting into the video signals, and so I think that just a high pass filter would get rid of a lot of that if it's properly done. And that's the big deal.
Guy, maybe Bob could just spend a little bit more time on his robust mean methodology, but I think the way he does the robust mean is going to be good enough for our work. Bob, maybe you could just highlight that robust mean calculation that you do a little bit more detail.
I'm not sure there's much that I can say in a casual way. Let's just look at what. So this is this is the robust mean using Finder aperture. You can kind of see what it's doing. I try to find all the pixels that I think belong to the background. This little red line shows the decision I made. I said everything to the left, this direction, is background, and everything above that comes from a star or background noise that was just above 1 sigma. I think that's what I'm using. And so this is the histogram, and it shows that there really weren't a lot compared to all of the background. So I look at every pixel that is in the aperture. So everything that is inside this green box, I analyze for computing the background. And I don't see any obvious artifacts of the visual striping effect, the horizontal striping effect that we see. And in any case, I have to use the data that's there frame to frame anyway. If you were to try to pre-process this like the Pluto people do, you would take the AVI and you would probably convert it to fits, and then you would look at it on a row by row basis, and you would adjust you would apply whatever filter. A high pass filter is probably the first thing you'd look at, and you would remove any high frequency noise, and then you would figure out what the mean value was, and then you would adjust all of the other rows in your frame to have the same mean background, and you would do that for every frame, and then you would record it, and then you would begin your processing. So if you were to do that, I would be processing data that had already been pre-processed, and I don't do any pre-processing. I don't know if that really helps. My gut feel is that those horizontal stripes don't cause any difficulties at all in producing light curves. It's kind of, although it's visually apparent, it's pretty small compared to the signals that we had available, at least for this video.
Bob, while you're there, why don't you move to that red box to the right with multiple stars in it so you can demonstrate how the robust mean deals with background stars in the aperture.
Yeah, so here we had a finder image, and in the finder image, it's obvious that there are some background stars. There's probably one here, there's clearly one here and here and here, in addition to the brightest star. So if I plot the robust mean, you'll see, yeah, there is stuff. Yeah, there's some stuff up here. And these are probably those little companion stars that we saw. So that would probably be this and this and this are showing up as these little peaks, but they're not affecting. I clipped them off. The red line says I'm not counting them. I'm not using them in the background calculation. Probably it's worth noting that this is a QHY that is running. You notice all the gaps? Those are pixel values that never occur, and they don't ever occur in part because it's a 12-bit or maybe 13-bit. It's a 12-bit camera where the 12 bits are shifted to the high order bits and treated as 16 bits. Well, that means that the low order 4 bits are filled with zeros, and so those are gaps. Let me say that was one of the things that gave me, excuse the pun, fits. I had an algorithm earlier that assumed some things about the distribution of pixel values, that they were kind of Gaussian and continuous. And when this particular video showed up, it showed the dangers of making any assumptions whatsoever about the distribution of pixel values in your background. I think I am now extraordinarily robust. This particular video now no longer gives me any problems in calculating the background values. Thanks for that, George, by the way.
Bob, I want to thank you for this presentation. I think it's probably time for us to adjourn for lunch.
Okay, I'm going to stop sharing.
But this was very, very instructive.